All right, well, without the review type of aspect, I figured today we'll talk about synthesis techniques, where we're looking at how to synthesize molecules. And what we've been really looking at majority of the semester when we've been talking about reactions is kind of one-step transformations. And, we've looked at them and said, well, we can do something like this and get our reaction to happen, and we'll get our product out and we're done. And that's that. And we've looked in some of our homeworks very briefly at doing multiple steps. Where we said we'll maybe have, okay, well, let's say we had say we wanted to do something like this. And it may not be so simple as doing one step. Because in synthesis, we always want our major product to be the one that's going to lead us forward. And so this is something that's just one step. But something like this is going to be multi-step. And how do we know that is because we don't know one way to get as a major product from our alkene to a bromine on the secondary position. All right, we do not know how to do this in one step. And so it must be a multi-step problem. And so we have to consider, okay, well, we know how to make bromides. And so we have to think, okay, well, what are the ways we do know how to make bromides? Well, it's always the best idea to look at the last part here. We always focus on the end of the problem, and then we can think about how to go from the beginning to the end. We just want to focus on the end. How do we make bromides? Specifically a bromide at that position. Well, we have a couple options. Well, we know we can take hydroxide, and that'll get us the bromide. We also know we can take an alkene, with the presence of peroxides will get us there. And then we think, okay, well, of those, which is going to be easier for us to go? We know how to make alcohols. We can make alcohols from alkenes or ketones or aldehydes or bromides. We can do all of these sorts of things, right? And so with these, it's kind of a matter of taking a look at all of the different possibilities for us to figure this out. We could say, okay, well, if we want to go the alcohol route, we then ask ourselves, okay, how do we make alcohols then? And so we'll take a look at alkenes in a second. Well, we know how to make alcohols, right? We can say, okay, well, all the ways we can make alcohols. Well, we can take a bromide and treat it with NaOH in like acetone or something. Do an SN2, and now we'll do that. Of course, this is ridiculous, because if our intended product has the bromine there already, like this is completely nonsense to take that product, treat it with NaOH, and then treat it with PBr3. It's like we're going in circles. Not efficient. We can make alcohols from alkenes. we can do this. We could also take a ketone and reduce it. That would get us to our alcohol. Those are kind of the main ways we know how to make alcohols. So if we're considering this, these are not really efficient, right? The most likely candidate is this one, because the only way we know how to make a ketone is by oxidizing an alcohol. So that's out of the picture. No good. Of course, this one is also no good because that's taking our product that we're looking for and turning it into something else. So that's not useful. But we saw that in our previous example, we saw, oh, well, this is another way to make the bromide from the alkene. And so it doesn't make sense for us to say, okay, well, we'll make the alcohol and then react it, but we're going to make the alcohol from the alkene. It doesn't make sense, right? Why would we waste this time going this route when we can just take an alkene directly and react it? So this means our most logical choice of synthetic route is using the alkene here. And so if we see, okay, well, how do we make this alkene? How do we make this? Again, we have multiple ways. That's why it's super important at this point in the semester that you'll have kind of mastered the reagents and regiochemical and stereochemical outcomes of all of the reactions we studied, because you will not be able to do multi-step things if you can't do single-step things. So it's super important that this is a skill that you will have developed after mastering single-step things. All right, so how do we make this? Well, we can take an alcohol and dehydrate it. We can take another alcohol and dehydrate it. That would give us our product. We could take a bromine and eliminate it. We could take a different bromine and eliminate it. Oops. And again, I'm just going to tell us right now this one is not useful because, again, that's our product we're already looking for. So don't even bother thinking about that. So to make this alkane, we kind of have two options. We can either make it from an alcohol or from a bromine. And if we think about how to make alcohols, we again have the problem of the alcohols being we need to get them from alkenes or alkyl halides already. So not so useful. So our main way of doing this will be to go from the alkyl halide. Those are easy to make. We can make them from alkanes, but we can't make these alcohols very easily. So our logical choice then is to use the alkyl halide here. And so then the last step is how do we make that? And thankfully we only know one way to do it, and this way is something that we are familiar with. If we take bromine in light, we can end up brominating that position selectively as the major product. And so we see that we went through a number of different reactions. And we ended up with our product of interest. And so we went through 3 steps to make this product. And in order to do those 3 steps, we had to learn all of those reactions we've talked about before. And we had options, but we saw that some options are nonsensical. Like, why would we start with the alcohol there, and do PBr3? And it's like, well, the only way we know how to do that is from an alkene or from an alkyl halide already. So a lot of the stuff you have to think about, how do we do this in the fewest number of steps, guaranteeing that our intermediates at each step is the major product of that reaction. So the overall goals, let's try that again, for synthesis is do it in the fewest steps possible, and then we also need each reaction or each intermediate is the major product. So, I mean, it doesn't really make a lot of sense if we're wanting this to happen, but our major product is something else. It's very inefficient to say, okay, well, I'm going to lose 3/4 of my product as the major product, and I'm going to take just a little bit of that and move on with my synthesis. You've just destroyed your yield. Terrible. So you always want to do this in the fewest number of steps, and you want to kind of make sure that your intermediate is the major product of each reaction that you do. So notice with these 3 reactions, our major product is the intermediate or product given. So the product of brominating with UV light is the tertiary position. So that's our major product. And then if we eliminate, the Zaitsev product is our major product. And then the anti-Markovnikov bromination is the major product using the peroxide in HBr. So each step, we're making sure that our major product is the one that we're making. And then we always want to do it in the fewest number of steps possible. Because yes, you could do something like this. Like, you could go crazy. Yeah, you could do something like this, but look at how many steps this is. 1, 2, 3, 4, 5, 6 steps. And so this synthesis pathway is much less efficient. I mean, it really makes no sense to do this step at all, when you can go directly from this bromide to the alkene directly, right? It makes no sense to have extra intermediates here. So you should always strive for the most efficient route possible. Always do it so that your product is one that's leading you in the right direction. Because going this hydroxy route is extraneous. We're going out of our way to make a hydroxy when there's no need to do so. So again, this comes down to your mastery of all of the individual single reactions in order to combine them in your head and be like, well, I know how to get from this to this. I know which reagents will get me there. So this is an inefficient synthesis, which will make us very sad. So don't do this. So this is 6 steps. That's twice as many steps. So not only is it more work, we're also producing more hazardous waste. We're also losing more of our product. each reaction has its own yield, right? Maybe a reaction is 90% yield. If all of these steps are 90% yield, we're going to lose a lot more product by the end of it than we would have made with a more efficient synthesis. So it's all a matter of doing it in the fewest number of steps and also making sure that your product is the major product of each reaction that you're doing. So that's all a matter of what this is. And so with all this sort of thing, when you're looking at a synthesis problem, you're asking yourselves two questions. Ask yourself two things. Number one, what functional groups have changed? And so that would be like, do we have a bromine here that's now moved over here? Do we have an alkene that's turned into an alkyne? Do we have an alkyne that has turned into an alcohol? It's important to analyze what functional groups have changed, because those are going to be where your chemistry is happening. Right? We don't have chemistry happening on alkanes very much. All we can do is brominate them. And so all the chemistry that's happening is happening at your alkyl halide, at your alkene, at your alkyne, at your alcohol, at your ketone, whatever. Functional groups are where the stuff happens. So if you can analyze what's happening within those functional groups, that'll be kind of the first step here. And then the other part to consider is has the carbon skeleton changed? And that's going to be, have we added carbons? Have we removed carbons? We're looking at how the carbons have changed. So functional groups is the first question. And then we're looking at how has the carbon skeleton changed. And number two is going to be a little bit easier because we only have a few questions or a few reactions that mess with your carbon skeleton. If we have more carbons in our product, we have two ways to do that. We added an acetylide or a Grignard. Those are the only two ways we have to add carbons to structures so far. Those are the only two ways we have to add carbons to our structure. And we can add as many as we want. Your acetylide could have 4 carbons, it could have 8 carbons, however long your acetylide is going to be. Although it is typically a fewer number of carbons. A Grignard reagent will also have as many carbons as you want. You can have a propyl Grignard reagent, you could have a methyl one. Either way, it works out. So we can see if the carbon skeleton has changed. So if we're adding carbons, the only way to do that is to use an acetylide or a Grignard reagent. If we have fewer carbons, that's oxidative cleavage. That's the only way we have so far to remove carbons from our structure. So we would use ozonolysis or KMNO4, cleave an alkene, and go from there. So that's the way we would remove carbon. So if we have fewer carbons in our product, we have to have removed one through oxidative cleavage, one or more. if we have more carbons than we started with, then we've either added an acetylide or a Grignard to our product here. And so if we want to think about this, well, how would we go from our butanol to this 7-heptanol? Sorry, this 4-heptanol. Why did I say 7? I know why I said 7, because it's heptanol. But how might we do this? So, as always, we have to think, how do we make secondary alcohols? And we see here that in terms of functional groups, nothing has changed in our molecule. We have an alcohol in both of them. However, we have a carbon skeleton change happening here. And so we have more carbons than we've done before. So we either need to use an acetylide or a Grignard reagent to make this happen. And we're going to see that Grignards are more common to make alcohols, and acetylides are more used to make other functional groups. So Grignard is our one of choice with alcohols, because we know that Grignard attacking a ketone or aldehyde will produce an alcohol. All right, yes, technically we can take an acetylide, add that onto something, and we can get that. Yes, that would work. So if we want to look at this, we always go in reverse, by the way. We always look at the product and think, how do we make that product? And then we work our way backwards to our starting material. And so with this one, we can say, okay, well, let's take those 4 carbons as an aldehyde. And if we put 1, 2, 3 carbons, that would get us to this product if we take that aldehyde with the Grignard reagent. If we want to add an acetylide, we could, but we're going to have to do more steps later on. We could say, okay, well, let's take 1, 2, 3, 4. We're going to have to take an acetylide. We're going to have to say, okay, we've got this propine ion with the sodium, and we're going to get that there, but then we're going to have a triple bond to deal with, and we're not going to get an alcohol directly. So probably less useful, because we're going to have to do a lot more stuff to then take that alkyne now that we have. We're going to have to do some hydroboration, oxidation, and then reduction. So it's even more steps. So generally speaking, when you have an alcohol and you've added carbons, Grignard is the way to go. All right, so we then just need to think, okay, well, you know how to make this aldehyde. That aldehyde has just come from taking our alcohol and using DMP on it. Rather, I've gone the wrong direction there. And from there, we can make our aldehyde from our original starting material. And then from that aldehyde, we can use a Grignard reagent to add the 3 extra carbons. And so, again, you have 2 choices of when you're adding carbons. You can either use a Grignard or you can use an acetylide. Grignards are better when alcohols are involved in your product or in your starting material, because we know how to oxidize alcohols to carbonyls, and we know carbonyls are reactive with Grignard reagents. So, when alcohols use a Grignard to add carbons, That's kind of the main idea here. So you want to use Grignard reagents with alcohols to add carbons. And of course, you'll need to oxidize something first, and then you'll need an acid wash at the end to get your alcohol out. We're going to see that if we have something like something like this, since we don't necessarily have an alcohol in our product, it's a little bit tougher to say we should use the Grignard. You can use the Grignard. It would technically work, and you just dehydrate it. But we can use the acetylide here as well. So you can use either one. So in this case, if we wanted to use the acetylide, we could do that. Because we know how to take an acetylide and get a transalkene. Or let's say specifically we want the cisalkene. In that case, the Grignard is not going to be the best way to go. Cisalkene cannot be made using a Grignard reagent. Grignard will give you an alcohol, and if you remove that alcohol, you're going to get the trans product as your major product. So cisalkenes can only be made from alkynes. And so again, we look at it backwards. A cisalkene as a major product can only come from an alkyne. And if we think 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. In order to get this, you have to use hydrogen and Lindlar. That's the only way to make a cisalkene as your major product. Lindlar will stop you at the cisalkene. And so now we have to consider how are we going to make this alkyne. And so we see we do have an added number of carbons. We've added 3 more carbons to this. 4 more. Have I added too many? 1, 2, 3, 4, 5, 6, 7. No, I have the right number of carbons. Well, this must have come from something with 1, 2, 3, 4. Oh, okay, hold up. I've got to 4. Yeah, sorry, we've got to fix this just a little bit. There we go. Too many carbons on that one. So with this, I have to fix this one too. If we want these to come together, we're going to have to use an acetylide. And so we have to think, okay, well, we have an alcohol to start. How do we turn that into a leaving group? Got a couple options here. We have 3 options, actually, we could do. We could say, okay, I'm going to take it with thionyl chloride and pyridine, make that into the chloride. Or I can take it with PBr3 and make it the bromide, or I can tosylate it. Any one of these will work. And so that's the benefit of synthesis, is that you have many options. And so if we take any one of these things and combine it with the acetylide, we can get that to work. So we can go through any of these steps here. We can say, okay, well, step 1, I want to use the thionyl chloride and the pyridine because I felt like it. I could use the PBr3, I could use the tosyl chloride, doesn't matter. Next, we're going to use our acetylide. After that, we're going to go ahead and use our Lindlars. with our hydrogen gas, and we will end up with our cis alkene. Only way to make the cis alkene is in major product is from an alkyne and Lindlar's. So all of this stuff you have to ask yourself, how do I make this product? And then from there, we are looking at adding carbons or messing with functional groups. That's all synthesis is. However, it is not easy because now we have to put in all of these things together into our reactions. So it's not a very easy thing to do. We should review some important alkyne making reactions. Let's just review this. If we want to review how to make acetylides, we'll start with an alkane. You'll brominate it. You'll eliminate. You'll dibrominate. Then you can use excess base. And if you use excess base, you'll actually end up with your acetylide already. And so that would be how you do that. So you start with your alkane. Have however many carbons you're adding on. In this case, it's 3 carbons. In the last case, I had 4 carbons. So if I asked you to also synthesize the acetylide, you would use butane instead and do the same set of reactions. You'd see that you would brominate, eliminate, dibrominate, and then di-eliminate. Of course, you'd want heat with both of these, and then you'd end up with your acetylide ion. And so through this, you'll end up making your acetylide, which then you can use as a nucleophile. It'll attack a leaving group, kick it out, and you'll end up with your new acetylide there. How to make Grignards. This one's fairly simple. Start with an alkane. And it really depends what Grignard you want. If you want this isopropyl one, you would just put it with magnesium and diethyl ether. And you now have your Grignard reagent ready to go. However, if you wanted the primary position instead of this secondary one, you would have to eliminate. And then you'd have to do an anti-Markovnikov bromination. And then you can add your magnesium and your diethyl ether. Oops. And you will end up now with your Grignard reagent on that primary position. So it depends which one you want. You may need to eliminate, you may not. So these are 2 different ones. And so it just depends what you want. If you're adding an isopropyl group versus a regular propyl group, you'll have to choose your Grignard reagent appropriately. And so let's say you have if you want this one, it simply depends which side you're starting with. You can make this from 2 ways. You can say, okay, I've got this aldehyde plus an isopropyl Grignard. Oops. Or we've got that aldehyde plus an ethyl Grignard. Either way will work. And so it just depends which one is going to be closer to your starting material. Both of these will give you this product. And in that case, we're looking at two options. We're either looking at it at that side, or that will give us this blue pathway, or we're looking at it attacking on the other side, and that would be the purple pathway. And so it simply depends. If you're starting with this thing, then of course it would make sense to do the blue pathway, right? Because that's very similar to your aldehyde. Purple pathway would be a lot harder to do, starting with this alcohol. So it'd be a lot easier to use a different Grignard reagent. So if this was your starting material, blue will be the way to go. If you had the other one, if this was your starting material, the purple pathway is better. Because we're just looking at kind of which side is closer to our starting material. And so it's, again, just more things to keep in mind as you're looking at these, is which way is going to be the most efficient to get me to that product that I'm looking for. And I could make this even worse for you. I can say we're going to start with this thing. And I want now this product. Yikes. Well, we simply need to consider that we can have either one. We can have it as, let me see, which side did I use purple on before? That was having it on this side. We can either have these two carbons attack the aldehyde, although this doesn't make sense, or we can have the 3 carbons here attack an aldehyde, and that side's going to make more sense, and we'll see why. So if we consider this, if we know how to make, we have 2 options. We had, which one, the isopropyl Grignard, or we had the aldehyde there. So you have to consider yourself, okay, looking at that starting material as propane, is there a way for us to very easily make propane on this? And, or like, which of these aldehydes is going to be easier to synthesize from our given starting material? We have 2 options here, and we're going to see that this one is easier to synthesize from propane. The reason is because the number of carbons is the same. That's the main reason. We also know that if we wanted this other thing, we're going to have to use some carbon adding agent. We would need to add another carbon to that right set of reagents where we had that methyl butanal or propanal. That would be a little bit harder to make. So this propanal is easier to make from our starting material because it's got the same number of carbons. And so this is not going to be efficient on that side. So we think, how do we make this? Well, we know we can make aldehydes from alcohols and DMP, or SWERN, or PCC. Any of those. And think, how do we make alcohols? Well, we can make alcohols from alkenes or alkyl halides. If we do it this side, it's it's BH3, THF, NaOH, H2O2. On the other side, it's NaOH. And so we want to think, okay, from there, let's see, how do we make these things? How do we make the alkyne? Alkene? How do we make the brominated species? Well, we know how to make this brominated species by doing HBr and peroxides. We know how to make this from the bromine. We would just use NaOMe and heat. And then we have to think how to make these two. Well, which is the better way? Well, obviously we see here that this alkene here is going to lead us to more steps. So it doesn't make sense to use this one, because if we already have the alkene, we can make it to the alcohol pretty easily. So it doesn't make sense for us to make the bromine and then hope to get as the alcohol. So a little bit easier here, and then of course this is just from the propane using light and the bromine. That'll get us to where we need to go. So because we've encountered this alkene here, we would still need to make the alkene in the other one, but we can go directly from the alkene to this hydroxide, the alcohol rather. If we try to use the bromine, that's going to take longer because we would have to make the alkene anyway. So if you can go directly from one functional group to another, that's always more efficient. It doesn't make sense to go between functional groups if that adds extra steps to your synthesis. I mean, yeah, you can then go, well, why don't we make this into a chloride and then to an iodide and then to an alcohol? Like, why would you do that? You're just wasting steps. Like, there's really no reason to do that. So you always want to do it in the fewest steps possible. Always, always, always. So, any questions so far on this idea? Let's do some problems from the book. A lot of these skills are outlined in Chapter 11. Although Chapter 11 does not include Grignards yet, so you'll still need those as part of your toolkit. Here's one. Yeah, let's do this. All right. And what are we making with this in Alkyne? Often synthesis problems will have multiple arrows. That's to indicate it's a synthesis problem that's going to take more than one step. We obviously do not know a single step that will take us from an alcohol to an alkyne, right? That's pretty obvious. So we have to always work backwards. That's always the key to these things. Let's take a look at it and ask ourselves what's different with the functional groups. What's different with the carbon chain here? Obviously, we can see from functional group standpoint, we've gone from an alcohol to an alkyne. And in terms of carbons, we have, let's just count our carbons. We have 6 carbons there. 6 carbons in our product. So we have no carbons added or removed. And our functional group has gone from an alcohol to an alkyne. That's what's happened in this reaction. That's always the first thing you want to do, is take a look at what's changed overall in terms of functional groups and then in terms of carbons. So we have no carbons changing in here. We've only got functional group changes. So we have to think, how the heck do we get from an alcohol to an alkyne? Right? And we don't want to ever think about that in one step, because this is something that's going to take multiple steps. And so we have to look at this product and say, how do we make the product? And if we want to think about alkynes, the only way for us to make them is to eliminate. So this idea is called retrosynthetic analysis. And we use special arrows for this. We use this kind of double-lined arrow to indicate that we're going backwards. And so we have three options for how to make this alkyne, right? And this alkyne can be made from, it's got to be a dibromide, right? Or a dihalide, I suppose, but bromine is our halogen of choice typically. So we're either going to need geminal bromides there, or a bromine on each one, or we're going to need two bromines there. And to make geminal dibromides is very tough. We do not know an easy way to do that. At least not. I mean, we know how to do it from an alkyne, but if we're trying to get to an alkyne, it doesn't make sense to have a geminal dibromide already. So this is our best choice here, because we know how to make this from an alkene. The other two have to be made from an alkyne, and so that's not going to be useful for us, right? If we're trying to make an alkyne, why would we have that same alkyne already somewhere else in our synthetic pathway? So we're going to choose the vicinal dibromide instead. And we know that we can make this dibromide from an alkene. We know how to do that. We know that this would just be Br2 and CCl4. So even though the arrow is going the wrong direction, we can still use our reagents and stuff on those arrows. So we're going backwards in terms of our synthesis route, but we're still going to put all those reagents there so we can see them for later. All right, so we've got our alkene now. How the heck do we get an alkene? Well, given our starting material is an alcohol, it would make sense that we would want to figure out a way to make that alkene from that alcohol. And we can do that by taking a look at the tosylate version and just using a base. We can eliminate to make that alkene. We're probably not going to want to use sulfuric acid, because that's going to make a carbocation. We would end up with a secondary carbocation next to a quaternary center. That is where we'll have methide shifts happening. We're going to destroy our molecule, and so let's not do that. So with synthetic pathways, it's generally better to avoid carbocations unless there's no rearrangements possible. And so we can figure this out by then just going ahead and we'll have our OH, which is our starting material. So you use tosyl chloride and pyridine. You could instead of using the tosylate, you could use a bromide or chloride. Either one of those would work. We could take the chloride. That's not a problem. Or the bromide. Again, synthesis, there's often multiple ways that you can get this to work. So you can get this reaction to happen. You can form your leaving group in any way you want. There are 3 ways to do that, making it into a leaving group. And then you'd eliminate, giving you the alkene. The alkene can give you the dibromide, and then you can eliminate both of them to make the alkyne. So it's simply a matter of figuring out how to make your product. What's the one way you know how, or one or a couple ways you know how to make your ending functional group. And after that, you have to think, okay, well, this thing, do we know how to make this? Do we know how to make a dibromide? Do we know how to make geminal dibromides? We don't. Unless it's from an alkyne, which again is not productive. We can't just go in circles with synthesis. So better to use the vicinal bromides there. And that must come from an alkene. We know how to make alkenes from alcohol. We would do an elimination to make an alkene, right? We would make sure that this is not a... we need this to not form a carbocation, so we're going to want to use an aprotic solvent here, so we should probably put that. Let's use acetone, so we can get an E2 reaction to happen here. And we know how to make that alcohol into a leaving group by 3 different ways now. Tosylate, brominate, or chlorinate. Any of those will work as elimination substrates. All right, so does that kind of work for us? We can look at a few more problems. All right. Any questions on that one before we do a few more? Okay. All right. Alrighty, so now this is an interesting one. Alright, so let's look at functional groups. We've gone from a cis alkene to a trans alkene. Not very helpful, but we have one more carbon here. And so this is the interesting part. So, with this, how the heck are we going to do this? Well, let's take a look. How do we make a transalkene? And notice we have one more carbon. So, probably we will have needed, and since we have no alcohols around, we've either done a Grignard or a... acetylide, there we go. We know how to make transalkenes. We have several options again. several options. We can say, well, we've taken this, we've done an elimination with a leaving group there on that position using a small base, or we've taken an acetylide and on either case we have two options. Our acetylide would have given us the, or we would use Na and ammonia. Sodium and ammonia would give us the trans-alkene. Or we would need to do an E2 reaction using a small base on something with a leaving group. And so we have to then choose now which of these pathways is more likely to get us where we need to go. Well, in consideration that we have an extra carbon in our molecule, we can do that using acetylides, right? Acetylides are a way to add carbons to molecules. And so it's probably less likely that we used this one on the left. So I'm going to say that this is probably less likely. Or it'll be harder because the acetylide already will have added the carbon for us. So having the alkyne there is beneficial because we know we have to have that extra carbon there somehow. So that would work. That being said, let's not worry about that. I'll show you another way to do this. So if we want to go the acetylide route, then we just have to think, how the heck do we make this acetylide? Or rather, this alkyne. And so we have to think, okay, well, two ways to make this alkyne. We would break it on either side and be like, okay, well, we need either this or we need on that side. In that case, we would use in either case, this would be the combination of things that would get us to where we need to go. So we're either adding our acetylide to an alkyl halide, right? That's what we're doing. We have two sets that would get this to work. We can break it on either side of the alkyne. We can either use cyclohexyl bromide and propyne, or we can use this cyclohexanal, this alkyne that's on the cyclohexane, and with a methyl bromide. And so, if we think back to our original molecule, which of these is closer? This has the same number of carbons, right? So this is going to be the better pathway. And so we'll just need to first do NaNH2. Second step, methyl bromide. There goes the book. So remember, always try and choose the ones that are more similar to your original things. How are we going to make this cyclohexyl bromide from this thing? We'd have to cleave it and then do some reduction and then do a bromination. Too many steps. Too many steps. So easier is to use the one that's got the same number of carbons as your original molecule. And so now it's simply a matter of going from this alkene to this alkyne. Alkynes, as we know, the best way to make alkynes is to take a dibromide. Again, we've just gone over this, so we're going to say that it's the we're going to go ahead and say that we're going to use the vicinal ones. We're not going to use geminal dibromides because those are not easy to make unless we have an alkyne already. Once we have that, well, we know that this comes from Br2 and CCl4. using an alkene, does that have 6 carbons? Kind of. And then we know how to make this alkene by eliminating using a bulky base from your original bromide. And that one we can get by simply doing our anti-Markovnikov bromination. So from there, it's simply a matter of working backwards. So how do you make each of these things? Well, we know how to make alkenes. We do that from elimination, right? And so we knew we had to eliminate from either bromide. Of course, yes, we have the other option where we have this one. Sorry, one more carbon. But not productive because we don't know how to make that one except from the same material. So always a matter of looking at which intermediates are more appropriate. Doesn't make sense to use that primary bromide because the only way we know how to make that bromide is from that same alkene. So if we have to use that alkene to get there, this is the only way to make this bromide. We can't, and it's so silly because if we want to make that alkene, why would we already have it? It doesn't make sense. So it's simply a matter of making sure those choices kind of work together. All right, so that's really the idea here. We're looking at what functional groups have changed, and are we adding or removing carbons and that stuff. And this is an interesting one because in this case we're using our main substrate as our acetylide. Normally we're used to adding acetylides as a reagent. We have an alkyl halide already, and we're going to add the acetylide onto it. In this case, we're using the acetylide and we're adding a methyl group. So it can go either way. Same with your Grignard. If you have a Grignard and you want to attack formaldehyde or carbon dioxide, that would work. So it totally works. So this way works using the acetylide. We could have also done this Grignard with formaldehyde. That would add us one more carbon, and we would get an alcohol. And, sorry, I need another carbon here. Though this would be a little bit harder to make into the alkene. We would see that this is a harder way to go. This would be a way to add one more carbon using a Grignard reagent. But this alcohol here is a little bit harder to turn into your alkene of interest, because you'd have to... you would need to turn it into a leaving group, eliminate, then do a Markovnikov bromination, and then eliminate again. And that'll be harder to do. So it's a little bit harder. So a little bit harder there versus doing our acetylide. So this one was a little bit easier to use the acetylide instead, because then we can get directly to where we need to be, and then it was very easy to make our transalkene using the sodium and ammonia. So that'll get us a little bit more efficiently to where we need to be. So this one was easier for us, because it's a lot easier to go from that alkyne to the alkene rather than from the alcohol to the alkene. So in that case, it's easier to use the acetylide. And so again, this stuff takes practice. And as I've put on canvas a bunch of this stuff, let's take a look. Let's take a look at this. If we go to canvas real quick. Synthetic problem set under our practice here. Click it. A nice review of all of our reactions. So you have this all here. Hooray. You've got all of your reactions. Blah blah blah. It would be a good idea to do this using alkanes with 4 carbons or fewer as your starting materials. Or for some of them you'll use cyclohexane as well. So try that. Try all of these out. This is the culmination of OChem, is synthesis problems. If you can synthesize these, not only will it is its own useful skill, but you will master all of the reactions previously if you can figure out how to make these. Some of them, like N has an ester. We didn't necessarily talk about that because we're going to be talking about that one a little bit later on. And S and Q also have esters. I'll very briefly show you how to make those because it's still useful. Although this is a reaction we're going to cover far more in the future. So a good idea to practice with these things. All right, and there's some ethers in there too, so don't forget you know how to make ethers. Williamson is kind of our main way, so don't forget those videos on those. We're going to see that, by the way, in ester. If you put an alcohol and a carboxylic acid together, you get an ester. So I'm going to be covering this in the carboxylic acids chapter. Some people cover it in the alcohol chapter. I used to cover this in the alcohol chapter because it's technically you have an alcohol as one of your things. You can make the ester. Having the carbons of your carboxylic acid next to the carbonyl, and then the carbons of your alcohol next to the oxygen. So that's how you make esters. One way to make esters. And so you'll see that as some of these problems have esters. So if you can make a carboxylic acid, how to make carboxylic acids? Oxidative cleavage, or oxidizing a primary alcohol. Alcohols you make from normal ways you make alcohols, and then you can make the ester. So one more addition to your toolkit there. So all this stuff very useful for you to be able to work with. So just remember that an alcohol and an alkyl halide, if you use a nice base, sodium hydride for example, you'll get your ether. So those are useful as well. So some of those have ethers and esters, so just remember those ways as well. So that's up there. I'll be putting also worksheets for alcohols and alkynes up. I'm not going to collect those. I'm not going to give you any more homework. So that's that. And I still have a few of your exams to grade anyway, so I'll get with that. And then I'll put up your alkenes key as well. So I'm going to save our Grignard reaction lab for next semester as well. We'll just have that early on just so you can practice with that. And then don't forget also on Canvas, right at the very top, you have a couple of videos to watch. I think overall it's about 3 hours for all three. So it'll take you through ethers, epoxides, and then thiols as well. And so the first one, you'll skip the first 12 minutes. The last one, you'll finish at that 30-minute mark. So just keep that in mind. Okay, so that is that. So those are some synthesis strategies. I figured we'll go over those because you better believe those are going to be a huge part of your next semester's exam problems are synthesis problems. You may see some of these on your final, although they will probably not be 4 or 5 steps. They'll be a little bit easier than that. And you may have some on your next exam as well. So, but again, those will be easier ones. All right. Well, that's all I wanted to kind of go over since we didn't have any questions, since apparently only Jackson watched Monday's video so far. So if we have no questions, then I guess we'll just end here. Okay. Well, in that case, good luck. Happy Thanksgiving. Monday will be your exam, so alkenes, alkynes, alcohols. Fun stuff. Okay, take care.